Hello again. In this video we're going to continue with the concept of AC electricity, and we talked about how AC was generated by a conductor cutting across magnetic lines of force, and how that, unlike DC voltages that reach their maximum voltage value almost instantaneously and then maintain that same level of voltage throughout the circuit operation, with an AC voltage it's different, because as the conductors spin and they cut across the magnetic lines of force, they actually do so at different rates, and sometimes they're actually running the conductor may be running parallel and not cutting any across any lines of magnetic force, and so there's no voltage generated at all. And then as it rotates 90 degrees, it moves into a perpendicular position where it's cutting across the maximum number of lines of magnetic force, and this would generate the maximum voltage. And then the points in between will be at some voltage that's between the maximum voltage and zero voltage. We talked about how that this voltage could be represented, unlike the DC, where we have a straight line because we have a voltage that remains constant. With AC voltage, it's always changing, so it goes up to its maximum value on the positive side, and then only remains at that level for a second. Then it begins to decrease in value back down to 0 volts. Then it goes in the opposite direction, so now it goes into its maximum negative voltage, and it peaks out again in the negative side with the negative or opposite polarity, and then it goes back to 0. This produces a figure that's known as the sine wave. Now, there's a couple of terms that are useful to know with regard to this. This sine wave right here, this where it goes from its 0 to its maximum positive voltage, then back down to 0, and then to its its maximum negative voltage, and then back to 0, represents one complete rotation of the conductor within the magnetic magnetic field. Okay, this is called one cycle. Okay, where it goes to the maximum positive, back to 0, to the maximum negative voltage value, and back to 0. That is one cycle. Now we have a measure of cycles per second, and that measure is hertz. In other words, the word hertz is a unit of measure that represents the number of complete rotations of the conductor per second. So let's say that our generator is able to make 2 complete 360-degree rotations within 2 seconds. It would generate a waveform that looks something like this, where I have a peak positive, down to 0, peak negative voltage, back to 0, another peak positive, back to 0, another negative peak voltage, back to 0. And then if our generator was capable of doing that twice per second, then it would have a frequency of 2 cycles per second, or also referred to as 2 hertz. Okay, if you have a generator or any type of a signal that's able to change polarities 60 times per second, then it would have a frequency of 60 cycles per second, or you could also represent that with the designation of 60 hertz. Most of the electricity that is generated in the United States operates at 60 hertz. In other words, the generators that produce that electricity are able to make 60 complete revolutions or rotations per second, which has a frequency here again of 60 hertz. Okay, so frequency is a very useful concept to know. It just refers to the number of complete voltage or polarity changes from the positive maximum to the negative maximum back to 0 of a signal, of a given signal per second. If we had a signal that changed polarities 100,000 times each second, then it would have a frequency of 100,000 hertz. So you might have heard the term kilohertz. Kilohertz is used to refer to thousands of hertz per second, and then megahertz represents millions. So that's what those designations refer to. Now, one problem that arises when you're dealing with alternating current electricity is precisely because the voltage quantity is changing all the time. In other words, unlike the DC voltage where it maintains a constant level, we talked about our circuit where we had a 10 voltage that was reached instantaneously, and then the circuit maintained that same level of 10 volts until we opened the switch and current flow stops altogether. So how can we compare a signal which has an ever-changing level of voltage to one that is essentially a straight line? In other words, it maintains a constant level of voltage. Well, there's some useful measurements that we can take. For one thing, we can find out the instantaneous voltage at a given point along this line by using some basic trigonometry. So let's say that I wanted to find out what my voltage was at this 35 degrees of rotation. By the way, this line represents degrees of rotation. So right here would be your point of 0. This would be 90 degrees of rotation, 180 degrees of rotation, 270 degrees of rotation, and then 360. So this horizontal axis represents our the rotation of the conductor inside of the magnetic field, okay, starting at 0 degrees up to 360. The vertical line represents the amount of voltage that is generated as it moves throughout its cycle, or as it rotates. Well, let's say that we wanted to figure out what amount of voltage was generated right here at this point. We'll say what did I have here? 35 degrees of rotation. Well, all we have to do is take our maximum, and let's say that this signal generates a maximum or peak voltage of 10 volts. By the way, the maximum, and I think I referred to this in my previous video, this positive maximum right here is called the peak voltage, and then this would also be the peak voltage but in the negative direction, or in the negative half of the cycle. Okay, so if I want to find out what my voltage is at any given point along this wavy line, I can just take the maximum peak voltage and multiply that by the sine of the angle of rotation. So let's say that I want to find out what the instantaneous voltage is at 35 degrees of rotation. Well, all I have to do is take my 10 volts maximum, multiply that by the sine function. This is a trigonometry function. Most calculators have a sine button, so you just punch in the sine button, and then you put in your angle of rotation, which in this case would be 35 degrees, and we do that and we come up with a voltage of 5.735 volts, which means that if given a maximum peak voltage of 10 at 35 degrees of rotation, our generator is generating a voltage in the positive cycle of 5.735 volts. Okay, well, I guess knowing the instantaneous voltage is also somewhat useful, but it's really not all that useful if we want to compare the amount of power that's dissipated to that of a constant voltage source, in other words, a DC voltage source. So we have to find some quantity of measure that we can use that would be the equivalent of the amount of power that's generated by a constant voltage, because ultimately a constant voltage is easier to work with. And we can come up with an equivalent for AC signals, and that equivalent is called the root mean square, where you take the root mean square of all of the voltages that are generated along the waveform, and that comes out to this this value, which we can compare to the constant voltage of DC power. In other words, what we're saying is that, well, I think it may be easier to explain just with an example. Let's see, what did I do with that? Oh, here it is. Let's talk about the voltage that you get when you plug something into your wall. Now, most people have heard that referred to as 120 volts, and that's accurate. But keep in mind that because this is an AC signal, that the voltage is changing at any given instant all the time. In other words, it's not a constant 120 volts, but it is, the 120 volts is actually the root mean square value. Well, how do we find that? It's really not that difficult. What we're going to do is take, so let's look at this. In all actuality, when you plug into an outlet on your wall, you're plugging into an AC source that actually generates a peak voltage, not of 120 volts, but actually this top positive peak right here, in other words, where it reaches its maximum positive voltage, is 169.7 roughly volts. But if we take this maximum, this peak voltage, this peak positive, and by the way, it also peaks out at the same level in the negative direction. So down here at 270 degrees of rotation, we have a peak negative voltage of 169.7 as well. Well, that peak voltage is not very useful to us because it's only at that level for a second, or just a very short instant in the total cycle. So we want to find a voltage that would be an equivalent of as if this were hooked up to a constant DC value where the voltage doesn't change in quantity. And all we have to do here is to find our root mean square value, which is that constant value, is to take the peak voltage, in this case 169.7, multiply that by the 0.707, and that's going to give us our root mean square value of 120 volts. So what that means is, let's draw this on our graph. Represents roughly, what is it, 45 degrees, I think, of rotation, basically, is what it looks like. So what that means is, if you can see my dotted line right here, that this signal that I have that reaches a peak of 169.7 volts in one direction, drops down to 0, and then reaches a negative peak value of 169.7 volts, is going to be the same, generate the same power, dissipate the same amount of power, in other words, through a resistor as a constant voltage of 120. And that's where the RMS value comes from. And that's where the 120 volts comes from that you hear about when they say that that a wall socket provides 120 volts of power, basically, or of potential. Okay. Now, if for some reason we need to go in the reverse direction, so what I did to find this RMS value was I just took the peak voltage, in this case 169.7, so you'd have to know that peak voltage, and then multiply by 707, and that gives me my RMS value. But I could also go in the other way, the reverse, by just multiplying by the reciprocal of 0.707, which is 1.414. So if I know the RMS value, but I want to find out what the voltage peaks out at, in other words, what the maximum peak is, I would just take the RMS value, in this case 120 volts, multiply that by 1.414, and I should come up with something very close to 169.7 volts. Okay, so that's a little bit about how voltage works in an AC circuit. And the really cool thing about all of this is that we're producing this electricity, this constantly ever-changing quantity of voltage or potential, by just rotating a conductor within a magnetic field. So we will continue with this and talk about how that AC is used in an actual circuit, and about some of the different effects that we can generate with an AC circuit that you cannot generate using a constant or DC circuit where the polarity does not change. Thanks for listening.